the lunch break on this last day of Asiacrypt 2022. And welcome to the second session on practical cryptography. It's my pleasure to announce the first speaker, Julia Lan from Cornell Tech. And Julia, the floor is all yours.
Thank you. Okay, so my name is Julia, and today I'll be presenting authenticated encryption with key identification. And this is joint work with Paul Grubbs and Thomas Part. So let's begin by recalling the definition for authenticated encryption with associated data, or AAD. So here in this setting, we have two parties and they share a secret key. The sender wants to send a message to the recipient, so they choose a nonce and associated data, the plain text message, and then they encrypt the message using their secret key to produce the ciphertext. The sender can then send the nonce, associated data, and ciphertext to the recipient, who can then decrypt using their secret key to recover the plain text message. And in this setting, of course, we require that an adversary who sees the ciphertext and doesn't know the secret key won't be able to recover the plain text message. But notice that there are a couple of assumptions we're making with this model. The first assumption is that the adversary has no way of knowing or even guessing the secret key. So typically the security definitions we require in this setting are confidentiality and authenticity, which model the adversary is not knowing the secret key. And also the second assumption here is that decryption only ever gets a single secret key as input. But this model does not always capture how AAD is practiced. So for example, this first assumption about the adversary not knowing the secret key doesn't capture the security goal of key robustness. And this was first introduced for the symmetric encryption setting by Farshima and Oshie in 2017. Oh, can you hear me? Okay, thanks. At a high level, this security property states, or an AAD scheme is not key robust or key committing if an adversary can compute a nonce associated data and ciphertext such that two different keys can successfully decrypt the ciphertext. And recent work has shown that many AAD schemes do not meet the security property, and that this has shown real vulnerabilities in practice. And notice that this key robustness goal does not meet our first assumption because the adversary can choose the secret keys. So to go over some of these vulnerabilities, Grubbs et al. And Dotis et al. Showed attacks against Facebook Messenger's message ranking protocol. In prior work, we described a new class of attacks we called partitioning oracle attacks and showed how to exploit key robustness attacks in the opaque and implementations of the opaque password authenticated key exchange protocol, as well as Shadowsoft proxy servers. And lastly, Albertini et al. Showed how to exploit key robustness vulnerabilities in envelope encryption and subscribe with Google. So overall, we're seeing that there's real vulnerabilities in practice and that this model isn't capturing these. Moreover, when we look at the second assumption that decryption only ever gets a single secret key, we see that this doesn't actually always model how AAD is used in practice. So as one example, let's take a look at the Google Tink API. This is an open source cryptography library developed by Google. And when we look at how key management works in Tink, we'll see that Tink actually has users work not with single keys, but with key sets. And so decryption takes in a set of keys. But how does decryption know which key to use? So Tink's approach to this is to add a 5-byte prefix to each ciphertext, which acts as a key identifier. And Tink will then try to decrypt this key specified by the identifier first. If decryption fails, Tink will attempt to trial decrypt with raw keys, which in its model are keys without identifiers, until it finds a key that successfully decrypts. But it's unclear what security goals this achieves because this doesn't align with our model of AAD. Furthermore, we've seen attacks on these ad hoc implementations on sets of keys. So for instance, we showed that there were vulnerabilities with multi-user Shadowsocks. And Albertini et al. Showed that there were vulnerabilities with key management services when they use sets of keys. So altogether, it's really unclear what security properties these approaches achieve. And to date, there's been no formal investigation of key identification in the setting. So we remedy this by initiating the formal study of AAD that supports key identification by extending non-spaced AAD into this setting. And this talk will formalize a new cryptographic primitive that we call AAD with key identification, or AADKI. So now decryption takes in a vector of secret keys, and part of the decryption task is to identify the correct key before decrypting. We'll also introduce new security definitions for the AADKI setting. So in particular, our definitions allow an adversary to specify malicious keys to better model possible attacks. And finally, we'll analyze security of existing key identification approaches and suggest ones. So let's begin by looking at this AADKI primitive. An AADKI scheme is a triple of algorithms. The first is a key generation algorithm. So this takes as input a key label, and this can be a public application defined string, such as a uniform resource identifier that key management services might use. It outputs a key, which in our setting is a key label secret key 2. Encryption takes as input a key, nonce, associated data, and message, and it outputs, in addition to the ciphertext, a special key tag. So this can be used to help with identifying the key during decryption. And lastly, decryption takes as input a vector of keys, a nonce, associated data, a key tag, and a ciphertext. So in particular, notice here that we choose to model a vector of keys rather than a set of keys. This is to preserve information about the ordering of keys, which might affect the decryption outcome. If decryption succeeds, it returns the key that produced the resulting plaintext, in addition to the plaintext itself. Otherwise, it returns a special error symbol bot. So now let's talk about what AADKI correctness is. Let's first recall that an AAD scheme is correct if for any key, nonce, associated data, and message, it holds that when we encrypt over these inputs and then decrypt the resulting ciphertext with the original key, we get back the original plaintext with probability 1. But what does a correct AADKI scheme mean? How do we extend this into our setting? Well, as a strawman proposal, let's try this. An AADKI scheme is correct if for any key vector, nonce, associated data, and message, where in particular the key is in the key vector. It holds that when we encrypt the message with the key and then decrypt the resulting ciphertext using the key vector, we get back the original key and message with probability 1. But there's a problem here, which is that there could be another key in the key vector that can decrypt the ciphertext. So this cannot be an information theoretic guarantee. We expect overall an AADKI scheme, therefore, to function correctly if it returns the correct key, but this requires a computational definition. We therefore provide a simpler absolute correctness definition and rely on a key robustness definition to model this behavior instead. So an AADKI scheme is correct if the following conditions hold. The first says that for any key, nonce, associated data, and message, if we encrypt over these inputs and then decrypt the ciphertext with a key vector, including just that key, then we get back the original key and message with probability 1. So this really just translates to the traditional AAD correctness to the syntax of AADKI for decryption with a single key. Our next correctness condition simply says that decryption should only output a key that was in the key vector. And next, our last correctness condition says that if the decryption of the nonce, associated data, key tag, and ciphertext outputs some key k, any other key vector containing that key k should not fail to decrypt the ciphertext. This doesn't mean that decryption might return that key, just that decryption should not fail. So now that we've covered our correctness conditions, let's take a look at our key robustness definition in this setting. We extend the full robustness definition from Barsham et al. Into the setting, and our new definition is called KI-FROB. So here in our security game, we require the adversary to return 2 key vectors, K0 and K1, and the nonce associated data, key tag, and ciphertext. The adversary wins if, when decrypting the ciphertext under the 2 different key vectors, decryption is successful under both key vectors and the keys that were returned are distinct. So notice that key robustness guarantees that only a single key can be used to decrypt a given ciphertext. This functions partly as a correctness definition in the setting in a way. We expect that the key used to encrypt a plain text should be the only one to correctly decrypt the resulting ciphertext. And also, if different orderings of the same key vector cause different keys to be output, these two key vectors would give a KIFROB win. The important point here is that two different keys are returned. It doesn't matter the ordering of the set of keys as input. So our next security definition in this setting is an all-in-one confidentiality and integrity definition that we call KINAE. This extends an indistinguishability style security definition for AAD to AADKI. And in this game, we allow adversaries to query the decryption oracle with a key vector that includes both honest and malicious keys in any order to better capture the setting. We use a simulator-based definition to model this. We also specify a key anonymous version called KINAK. So let's look at some more specifics on this definition. The adversary goal here is to distinguish between a real and simulated world. The adversary has access to oracles to generate honest keys, to encrypt, and to decrypt. So we have two games here, KINAE1 and KINAE0. The first is the real world game, KINAE1, and this models interactions with the real scheme. KINAE0, our ideal world game, uses a stateful simulator to generate oracle outputs. So let's take a look also some more at the ideal game KINAE0. During encryption, we have two possible leakage functions. The first is a non-key anonymous leakage function. Here, the simulator receives both the game-generated key identifier and the plain text size. In our key anonymous leakage function, the simulator receives only the plain text size, so the simulator doesn't know which key is being used to encrypt. Decryption, recall, takes as input the vector of keys, which could be honest or malicious in any order. So here, we simulate this by first scanning through honest keys in the queried key vector. If the key and ciphertext were output from a prior call to the encryption oracle, then the associated plain text is returned. Otherwise, if this fails to find the key, and there are malicious keys in the key vector, the simulator is given ciphertext and remaining malicious keys to decrypt. So doing this allows our definition to imply a variant of ciphertext integrity for this setting. Now that we've covered our security definitions here, let's describe our approaches to AADKI. We specifically divide key identification into several categories and analyze their security. Our first approach is key labels. This assigns each key a static label, then prepends the label to each ciphertext it produces. And this is specifically parameterized by an AAD scheme. And there are a couple of examples of this in practice. So we talked about Google Tink before. There's also the Amazon Web Services key management service. They use a URL indicating where to fetch the key. This can be considered a type of key label. So more specifically, encryption calls the AAD scheme on the plaintext message. And as part of the associated data, we include the key label. The key label itself forms our key tag, which we output together with the ciphertext. Decryption then iterates through the key vector and checks if the key label for the key matches the key tag, in which case we'll try to decrypt with the AAD scheme. If this succeeds, then we'll simply return the key and message. So key labels are KIFROB secure if and only if the AAD scheme used is key robust. Key labels especially might not be unique, and therefore we can't use them for key commitment. Key labels are KINAE secure if the AAD scheme is key robust and multi-user AAD secure. And in particular, ciphertexts are prepended with static strings, so there's no key anonymity. If that's desired, however, you could use instead a trial decryption scheme, which is where key labels are simply empty and you iterate through every single key. This adds extra overhead, but it provides key anonymity. Okay, our next approach is static key identifiers. This computes a static identifier from the key and uses this with the key label as the key tag. This is also known as a key check value in practice. And this is parameterized by a key check value function, an encryption key derivation function, which is distinct from the key check value function, and an AAD scheme. So here during encryption, we compute from the key check value and the encryption key using the key derivation function. Our key tag is now formed by concatenating the key label together with the key check value. We encrypt using the AAD scheme, and then we return the key tag together with the ciphertext. For decryption, we iterate through the key vector, we compute the key check value and encryption key from each key. And then if the key label and key check value together for that key matches the input key tag, we'll attempt to decrypt with the AAD scheme. If that succeeds, we simply return the key and message. And we specifically divide static key identifiers into two subcategories: static key hints and static key commitments. For static key hints, the key check value is computed using a PRF. So these can be short and efficiently computed. However, they cannot be used to commit to a key. So they need to be used with a key robust AAD scheme to achieve KIFROB. The benefit of static key hints, however, is that they can be used in more bandwidth constrained environments when ciphertext links might need to be shorter. And of course, they don't provide key anonymity since the key label and key tag themselves are static. So there's a couple of examples of this used in practice. In general, they use something like AES or SHA-1 computation and then truncate that. Static key commitments instead compute the key check value using a collision resistant PRF. And these are longer and less efficient to compute than key hints. However, they can be used to commit to the key. So they can be used with a non-key robust AAD scheme to achieve KIFROB. These again do not provide key anonymity. And one example of this used in practice is the AWS encryption SDK's use of SHA-256 over the key. And our final approach is the dynamic key identifiers approach. This computes a dynamic identifier from the key and a nonce and uses this as the key tag. So notice that each time during decryption we use a key, we'll output a distinct key tag. This is the key anonymous counterpart to the static key identifiers approach. And to preserve anonymity, key labels will be empty. This is again parameterized by a key check value function, an encryption key derivation function, and an AAD scheme. So encryption now computes the key check value using a nonce, and the key check value itself is the key tag. Decryption will iterate again through the key vector, compute the key check value, and compare that to the input key tag. And if that matches, we'll try to decrypt with the AAD scheme. We again divide dynamic key identifiers into key hints and key commitments. As before, key hints are computed using a PRF and can be shorter and more efficiently computed. However, they cannot be used to commit to a key. So you need to use a key robust AAD scheme with this. Dynamic key commitments alternatively are computed using a collision resistant PRF and are longer and less efficient to compute than key hints. However, they can be used to commit to the key, so you can safely use a non-key robust AAD scheme with them. Both approaches do provide key anonymity. So here's a summary of our various approaches, and in particular, static key commitments and dynamic key commitments are two approaches that do not need to be used with a key robust AAD scheme. And trial decryption and dynamic key identifiers are, of course, our key anonymous approaches. So to conclude, the current model for AAD does not always capture how AAD is used in practice. We therefore introduce authenticated encryption with key identification, which allows key identification during the decryption step. We introduce new security definitions for the AAD KI setting, and we analyze the security of existing key identification approaches, as well as suggesting new ones. Thank you, and I have my email on here in case you want to chat more about this. You can also read the full version of this work on ePrint. I'm happy to take any questions.
Are there questions for Julia?
Hi, thank you for your talk. You had mentioned that key labels can be used for key identification and that for that to be AED KI, it would demand that the underlying AED scheme be key robust. Do we know of any schemes that achieve this? You spoke of Tink by Google. Is that key robust, the AED scheme?
It depends if they're using in key robust AED scheme. So in Tink, for instance, you might use it with AES-GCM, which is known to not be key robust, and then that case, you can't rely on the key label to commit to the key.
Okay, I'm sorry. I have a follow-up question. Is there a way that we can convert an AED scheme to be key robust AED?
There are a couple of techniques. So like one is, for instance, you could cache the key and then append that to the AED scheme. Some other approaches I've said to use, for instance, a plain text, like a block of zeros that you prepend to a plain text message and then you check that after decrypting. We can also talk online about various offline about various.
Thank you.
Are there any more questions? Yes. Oh, yeah.
Thanks for the talk, Julia. I have one question. When I saw it right, that in syntax, you separate those key tags from the ciphertext. Can you maybe comment on why? Like, why would one not want to consider the key tag part of the ciphertext, and it's kind of like a task of the decryption scheme to figure it out where to pull it from?
So this is following some of the AED syntax in authenticated encryption, which might have the authentication tag as separate from the ciphertext. You could change this so that you just output a ciphertext, but we wanted to like be more explicit about that you're outputting a special key tag as part of the ciphertext that should be used as part of the decryption step.
Okay. Does any of your construction kind of like need that it's syntactically spelled out, or could they all, in principle, retrieve it from the ciphertext?
You could also retrieve it from the ciphertext. I think we just wanted to be more explicit in order to highlight that this is an extra part of the ciphertext.
Okay, thanks.
Sure.
Any more questions? Let me take a quick look if I can see any questions in the chat here. I don't see any. I have one question. I mean, this work is clearly very much motivated from real world examples. So you mentioned Google Tink, AWS, KMS. Did you contact the teams at, say, Google and AWS? And if so, what was their reaction on this work?
Oh, we hadn't contacted them. I think it's not like we didn't find an actual vulnerability, so it didn't seem necessary to contact them, but we can. Like,
I mean, maybe they're interested to hear that you're actually looking into this. I mean, it's also positive results. They might actually be happy to hear, right?
Yes,
so,
definitely. Yeah, we should definitely consider that in the future.
Okay, thanks.
Thanks.
As I don't see any further questions, please join me in thanking Julia again. And then our next speaker, the next talk will be given remotely by Yo Lu from Shanghai Jiao Tong University. And
Okay.
Yo, the floor is all yours.
Oh, okay. Can you hear me?
Yes.
Okay. Hello, everyone. I'm Yu Lu from Shanghai Jiao Tong University. Today, I will share our work, Privacy-Preserving Authenticated Key Exchange in the Standard Model. This is a joint work with Shengli Liu, Shuai Han, and Da-Wu Gu. I will introduce our work from the following perspectives. First, I will talk about the definition of PPAKE and its security. Next, we will give our construction and analyze its security. Finally, we will give the conclusion and some future work. Now we recall the authenticated key exchange first. AKE allows two parties to authenticate each other and securely share a session key. It has been widely used in data sharing electronic notebooks. As shown in the left figure, user UI has long-term key SSKI, and user UJ has long-term key SSKJ. When they want to share a session key, they will send some messages to each other, and at last, they will agree on a session key. However, there is a problem. In some cases, the interacting parties may want their identity kept secret from others. However, their transcript sent in the channel may contain information about their identities. Thus, the concept of privacy-preserving authenticated key exchange is proposed. It requires anonymity, which means the adversary cannot identify the users who are communicating, even seeing their transcripts. Actually, most AKE protocols are not privacy-preserving. For example, the well-known SAND-DH protocol is not privacy-preserving. In SAND-Diffie-Hellman protocol, each party uses a Diffie-Hellman key exchange to agree on a session key and uses signatures to authenticate each other. The signature leaks the identity of both initiator and responder. The adversary can guess the initiator and responder's identity and check his guess by verifying the signature. To solve this problem, SSL20 proposed a way to protect the identity of users with PPAKE. It considers the server-to-server scenario. Let's focus on the left figure. In a server-to-server setting, both the initiator and the responder are agent servers, and behind each agent server, there sits many users. The adversary controls the server-to-server channel, but does not control the user-to-server channel. For example, if user U1 wants to start a session with user U4, instead of sending messages to U4 directly, it will send its message to its agent server A. Then the agent server A communicates with server B, and server B finally passes the message to the target user U4. Anonymity in this setting requires the adversary cannot distinguish which user sits behind the agent server, even if they can control the server-to-server channel. Now we recall the construction idea of SSL PPAKE. The protocol is also based on the Diffie-Hellman key exchange. When a session starts, both users first do an anonymous Diffie-Hellman key exchange to get an ephemeral key. Then they use this Diffie-Hellman key to encrypt the signature to hide their identity and authenticate each other. However, due to the lack of authenticity in the first two rounds, it suffers an active attack. If an adversary modifies the second message, then it shares the same Diffie-Hellman key with the initiator. After the initiator sends the third message, the adversary can decrypt the ciphertext and get the identity of the initiator. Besides, SSL PPAKE considers the server-to-server scenario and does not apply to the user-to-user scenario, like the scenario of WLAN, Bluetooth, or Apple's AirDrop. Hence, a question is how to design a PPAKE protocol for the user-to-user scenario. In the user-to-user scenario, there are no agent servers. We also consider the broadcast channel, just like the scenario of Bluetooth, WLAN, and AirDrop. The adversary can see the message in the broadcast channel and involve in the communication of users. Next, we introduce the security requirements for PPAKE in the user-to-user scenario. The explicit authentication means the active attack can be identified. For example, if the adversary changes the first message sent from UI to UJ, then UJ will reject this session at last with overwhelming probability. And for each accepted user UI, there is a unique partner UJ such that the output of UI is the input of UJ, and the output of UJ is the input of UI. In this example, if user UI and UJ are accepted, then it must hold M1 equal to M1 prime and M2 equal to M2 prime. Okay, forward security for session key means the session key is pseudo-random if there are no active attacks, even if the long-term key of users are leaked to the adversary. Anonymity requires, given the transcript, the adversary cannot distinguish which two users are communicating. The adversary can also involve in their communication by sending messages in the broadcast channel. Forward anonymity means the anonymity still holds even if the adversary corrupts these users after the adversary gets the transcript. For example, suppose the adversary gets the long-term key of user UJ1 and the transcript. Forward anonymity requires the adversary cannot determine whether user UJ1 was involved in the previous communication. Now, let's see what happens if we use SSL PPAKE in the user-to-user setting directly. Suppose user UI wants to communicate with user UJ2. She will first broadcast a G to the power of A to all of users. And to keep anonymity, the first message does not contain any information about its target recipient. Each user is not sure whether he is the target recipient after receiving the first message. So each user must reply with a G to the power of B. Now, user UI receives all the messages, but she is still not able to identify the right message sent from the intended party UJ2. To continue, UI has to compute all Diffie-Hellman keys and encrypt the signature with each Diffie-Hellman key. This will cause large communication and computation complexity. Moreover, the adversary can also send a G to the power of B. And then it can always decrypt one ciphertext and then determine the initiator's identity. So we need to design a new PPAKE protocol for the user-to-user setting. Our approach is to make PPAKE robust. We see a PPAKE protocol is robust if each user is able to ascertain that the message in the first round is for him or her. Any user except the target recipient will output failure when they receive the first round message of PPAKE. In this figure, user UI wants to talk to UJ2 and broadcasts the first message. Then, after receiving the first round message, only user UJ2 will reply for this message, and the other users will keep silent. With the robustness, the communication and computation complexity can be reduced. Next, we will introduce our construction. We propose a generic construction from a signature scheme, a key encapsulation mechanism, a message authentication code, and symmetric encryption. We will talk a bit more about CAM. We require the CAM for two more properties. One is anonymity, which means given the ciphertext C and two public keys, the adversary cannot determine the ciphertext C is generated by which public key. And the other property is robustness. If a ciphertext is generated by one public key, then using another secret key to decrypt it will output failure with overwhelming probability. Now we will introduce our construction. Suppose user UI is the initiator and its target recipient is user UJ2. It will first encapsulate a key K1 using the target's public key. Then it will broadcast a G to the power of A and the ciphertext C. After receiving the first message, each user tries to decapsulate the ciphertext C using its own secret key. And only user UJ2 will get K1. Other users will get a failure by the robustness of CAM. Next, user UJ2 computes a Diffie-Hellman key and uses K1 to authenticate the message it receives and the message it sends. The other users will keep silent during the process since they are not the target recipient. Then user UJ2 will broadcast G to the power of B and sigma. In the third round, user UI will check the validity of sigma and computes the same Diffie-Hellman key, derives key K2 to encrypt its identity and a signature, and then it will broadcast the ciphertext C. After receiving the ciphertext, user UJ2 decrypts C using K2 to get the identity of its initiator and the signature, and verify the signature. Finally, user UI and user UJ2 will share the same session key K3. Now we analyze our protocol's security. The authentication of responder relies on CAM and MAC. In this example, only user UJ2 can decrypt C to get K1 and generates the same sigma with user UI. And the authentication of initiator relies on the signature. Only user UI can generate the valid signature in the third round. And since all transcripts is signed by signature or tagged by MAC, the explicit authentication is ensured by our construction. Also, due to the explicit authentication, now there are no active attacks. Then the key pseudo-randomness is generated by the Diffie-Hellman key exchange protocol. Moreover, note that the session key is independent with the long-term key of both users. Our construction also has forward security. Now we discuss the anonymity of our construction. The initiator's identity information is only contained in the third round message, and this message is encrypted by the Diffie-Hellman key, so it is protected well. The responder's identity is only contained in the first round message. And due to the anonymity of CAM, the adversary cannot know the ciphertext C is encrypted by which public key. However, our construction can only achieve semi-forward anonymity for the responder. If the long-term key of user UJ2 is leaked, the adversary can decrypt the ciphertext C successfully. Then it can determine UJ2 is one of the responders in previous communications. This is a common problem for robust PPAKE. To achieve robustness, the first message must bind to the long-term key of the responder. Then, if the long-term key of user J is leaked, the adversary can check whether J is a target responder. At last, we will compare our work with some related work and give some future directions. Let's look at the table. This column means the communication complexity of the protocols, and this means the computation complexity of protocols. This means the number of rounds of the protocols, and this means whether the protocol has a forward security. This means whether the protocol has anonymity for initiator and for responder. This column means if the initiator was corrupted, then whether the anonymity still holds for the initiator and for the responder. And this means whether the protocol has mutual authentication. And this means the protocol is proved in the standard model or the random oracle model. Okay, compared with the first scheme, our protocol has mutual authentication and full anonymity. And the second protocol has no forward anonymity. And the SSL20 and RSW21 has large communication and computation complexity. To conclude, we propose a PPAKE scheme, especially for the broadcast channel and user-to-user setting. We also give a concrete installation based on DDH assumption. And we also leave an interesting problem that can we construct a PPAKE scheme that satisfies full forward anonymity in our model. Okay, thanks. That's all. Thank you for your attention. If there are any questions, welcome to questions.
Thank you very much for the nice talk. I hope that you could hear the applause. Are there questions from the audience? Well, while people are still raising their hands, I have actually two questions. So one is just for my understanding, the robustness notion that you need for the CAM. You said that the probability that another public key is able to, another secret key is able to decrypt is, so is that sort of a statistic notion, or is that an adversarial notion? As in, can I construct a different public key, or is that statistic? Does that question make sense?
Actually, I think in our construction, we only need the weak robustness, and we only I think
okay.
That just means we need to, if you encrypt the ciphertext using one public key, and then you use other secret key to decrypt it, will output failure, and with overwhelming probability.
Okay. Yeah, no, it's okay. I got it. Sorry. Let me see if there's more questions. Don't see any. There's one question that's maybe a bit of a mean question, but usually when you're doing anonymity protocols like on the internet, right, then you assume that sort of the network anonymity is given, for example, by people using Tor, and then you use the assumption that the network layer is anonymous. Now, the setting that you sketched is a local area network where just everyone is on the same Wi-Fi. Where on the network layer, you would just send your messages and they have a MAC address, and well, usually that identifies you, except if you randomize that one and probably do some more things. Are you aware of approaches that would sort of compose with the protocol layer anonymity and give you also network layer anonymity for, say, Wi-Fi or AirDrop, or what's the status there? Do you know?
I think our protocol needs the MAC address does not reveal the user's identity. Or, yeah, I think we rely on this. Or maybe you can not use the MAC address, maybe, since you,
All right. Okay, I don't see any further questions, so please join me in thanking you again.
Thank you.
Thank you for your talk.
Okay.
And we will move to the last talk of the session, which will also be given remotely. And I will wait for technology follow-up. It will be given by Jamin Sue from Shandong University. And don't see them yet.
Okay, you hear me?
All right, so the floor is all yours. Thank you.
Thanks for the introduction. I will give the talk on the field-based division property, applications to mimecy, festo mimecy, and G-mimecy. I'm Jiami Cui, and it is a joint work with Kai Hu, Meiqing Wang, and Pu Wenwei. So this presentation consists of 4 parts, and I will first give some background knowledge about the algebraically simple symmetric key primitives. So the main topic is the symmetric key primitives that are efficient in several applications like multi-party computation, fully homomorphic encryption, and zero-knowledge proof. Instead of the optimization for speed or memory consumption, we need to reconsider which operations are costly and which costs almost free in this case. So new cost metrics like low number of multiplications and low multiplicative depths are desired. And to be efficient, these primitives usually works over large binary extension field f2 to the n, or large prime field. Since the size of the field is large, the S-box cannot be pre-computed or pre-stored as in the traditional cipher. So we have a simple algebraic representation like power maps, x maps to x to the d, or the inverse of x. So as a result, these new primitives are often algebraically simple. There are a lot of examples like the Mimicy family, Hadis Mimicy, Vision and Rescue, Siminian, and more. Well, the impact of the property of arithmetic operations over large finite fields needs further study. Basically, these primitives are represented by simple algebraic representations, so they are vulnerable to algebraic attacks naturally. And attacks like Grosvenor basis attack and high-order differential attack have shown powerful against these primitives. We have Grosvenor basis attack on full-round Javas and Friday, and high-order differential attack on full-round Mimicy and G-Mimicy. So we came up with a natural question that, since the algebraic representation is significant to the cryptanalysis of these novel primitives, how can we better understand it? In this paper, we carefully studied the transition of the monomials, and we propose a new technique of studying the polynomial representation. It is called general monomial prediction, and it is an extension of division property over binary field to binary extension field. And using general monomial prediction, we propose a new algorithm dedicated for degree evaluation. And basically, this is benefit from the link between the binary field and the binary extension field. This leads to the improved integral distinguisher and zero-sum distinguisher on different instances of Mimicy, Festo Mimicy, and G-Mimicy. So first, we need to take a closer look at the polynomial representation. Consider a function f over f2 to the n. The input is about t variables, and the output is a single variable. The function can be described by a polynomial like this. Pi u x, or we called it x to the u, denotes a monomial, and phi u denotes a coefficient. With a non-zero coefficient, we see that the monomial pi u x is contained by f, and otherwise pi u x is not contained by f. We were using the following example to explain this. Given a polynomial f of x0 and x1, you can get the following two observations. x0 to the 7 times x1 to the 10 is contained by f, and x0 to the 11 times x1 is not contained by f. If the polynomial representation is simple, the problem to decide if x to the u is contained by y to the v is a trivial problem, just by simple calculation. But when the polynomial representation is complex or it is not available, as usual in the symmetric key primitives, this problem is a difficult problem. So this is why we propose general monomial prediction. The goal is to check whether x to the u is contained by y to the v when the polynomial representation is not available. This is achieved by decompose a complex function to a sequence of simple functions. Let xi and xi plus 1 denote the input and the output of the function f. Since we know the polynomial representation of fi, we can easily tell whether a monomial of xi is contained by the monomials of xi plus 1, and we can find the local transition. For an iron cipher, if we can successfully connect the local transition, we can find an iron transition, and it is called the general monomial trail. If we can detect one trail from the beginning to the end, we see that we do not know about whether there is some monomials of the beginning contained by the monomials of the end. Due to that, the trails may cancel each other out. But for example, if these trails are removed, in this case, there is no trail from the beginning to the end, and we know that there must be no monomials of the beginning in the monomials of the end, so we found a missing monomial. So let me explain general monomial prediction with the example here. Let z equals to 2 times y cubed, and y is a function of x0 and x1. We can compute the representation of y to the power of 3, 4, 5, and 7 and they all contain the monomials x0 to the power of 5. We can also compute the monomials of z, and here is the 4 monomial trials connecting x0 to the power of 5 and the monomials of z. Next, we show the propagation rules of general monomial prediction, and the propagation actually model the transition of the monomials, so it can be concluded as u can propagate to v if and only if the monomial x to the u is contained by y to the v. For the propagation, we have 4 rules for basic operations, XOR and copy power. For the XOR rules, we have the input is x0 and x1, and the output is y. Their corresponding propagation is u0, u1, and v. If we consider a valid propagation, it essentially means that the monomial x0 to the u0 times x1 to the u1 is contained by the monomial y to the v. So by simple calculation, we can know that the propagation rules is like here. And for AND rules, we have v is equal to u0 and u1. For copy rules, u is equal to a different modular addition of v0 and v1. Power rules is a specific rules over finite field, and y is defined as the dth power of x. As in the Boolean function, the highest degree is 1, so we do not have the power rule. And we have u is equal to the same modulo of d times v. So there is a comparison of our general monomial prediction and the word-based and bit-based division property. For the word-based and bit-based division property, the variables are often defined in bit level, and for our general monomial prediction, the variables are defined over fields. Since the word-based division property actually works at word level, it only exploits the algebraic degree information of the local components. So the local propagation is not so accurate. And for the bit-based division property, it uses the information of the inf of the Boolean function. And for our general monomial prediction, we also use the polynomial representation, and the local propagation is accurate. Before going to the evaluation of the algebraic degree, I want to talk about the high-order differential attack. High-order differential attack was proposed by Xue Jialai. Ek is a function with algebraic degree of delta, and P is a plaintext set. If the dimension of P is greater than delta, we have that the sum of all plaintexts over the set P is 0. So the goal is to detect the algebraic degree of the function Ek. So the basic strategy of how we detect the algebraic degree is that we observe the polynomial representation of the cipher and then convert the polynomial degree to the algebraic degree. The connection between the two kinds of degree is given a polynomial f here. The polynomial degree, denoted by the dag of f, is just the usual degree of the polynomial. The algebraic degree, denoted by delta f, is given by the maximum of the Hamming weight of exponents with non-zero coefficient. For example, let f be a function of x0 and x1. The polynomial degree is just the ordinary degree, 7 plus 10. That is 17. And since the Hamming weight of the two monomials is 4 and 5, the algebraic degree is 5. A cipher can be represented by a keyed polynomial y of plaintext x and the secret key k. So basically, our goal is to check whether y to the v contains the keyed monomial k to the w times x to the u of algebraic degree greater than d. The degree of k, that is the w, is set arbitrary since we only care about the degree of x. And if there is no such trial, there is no such monomials, and we know that the algebraic degree is less than or equal to d. But if there is a trial, we do not know any information about the monomial. When using STP solvers to detect the algebraic degree, we need to create the initial property and the final division property. The initial property is prepared as T variables. Each variable is a bit vector with length n. It actually means what kind of monomials you want to detect. Suppose if we want to check whether there is a kind of monomials with algebraic degree greater than d. We then set the sum of each bit of the initial property to be greater than d. And for the variable w, we set it arbitrary. The final division property is also t bit vectors of length n. The ith variable is set to 1 if we focus on the ith variable of the ciphertext, and other variable are 0. And run by the solvers, we can check if there is a monomial trail from the beginning to the end. If the solvers cannot find any trails, we know that the upper bound of the algebraic degree is d, and we can set the initial property to d-1 and continue to check to get a better bound. The applications of our algorithm is the Mimicy family. They all use x to the power of d as their round function. For Mimicy, we have the input x and some key k, and the round function is consist of key addition, constant addition, and usually a cube function as S-box. For Festo Mimicy, it follows the Festo structure, and for G-Mimicy EIF, it follows the unbalanced Festo structure, while the S-box is also a cubing function. This is a visualization of our results on Festo Mimicy with block size 129. And this line shows several bounds on the algebraic degree for Festo Mimicy. This horizontal red dashed line shows the maximum algebraic degree, and the red line shows the trivial upper bound, and the green line shows the trivial lower bound, and the blue line shows the bound detected by our algorithm using general monomial prediction. You can see that there are two phases of the degree growth. A phase of linear growth for the first stage, and followed by a phase with several large plateaus until reaching the maximal degree. Some plateaus only covers for a few rounds, while there is the largest plateau just before the maximal degree. The stage of the slow growth significantly influences the growth of the algebraic degree, and more rounds than previous predict are necessary to guarantee the security. The orange line shows a new theoretic bound proved in our paper on the algebraic degree for Festo Mimicy-like schemes. It also depicts the first phase of the linear growth. So here is the result of our algorithm. For Mimicy with block size 129, we present the exact algebraic degree when d is equal to 3. It is the same as the theoretic proof in the reason paper. When d equals to 2 to the L minus 1, we extend the distinguisher for 1 or 2 more rounds compared to the previous best work in Asiacrypt 2020. And for d equals to 2 to the L plus 1, we found distinguishers with lower data complexity. For Festo Mimicy with block size 129, the previous only attack for 83 rounds, but we can attack for 124 rounds. And we can also give a 4-round knowing-key zero-sum distinguisher. For G-Mimicy, we search for a 50-round high-order distinguisher for the instance with block size 33 and 8 branches. So this is the summary of our applications. And I will conclude my talk. We propose general monomial prediction, and this tool is used to detect the algebraic degree algebraic representation of the ciphers over F2 to the n. And by using this tool, we propose a new framework for degree evaluation, and we can no longer only rely on the theoretic proof to estimate the algebraic degree over the finite fields. So we get the best high-order distinguisher and zero-sum distinguisher for different instances of mimicy, festomimicy, and G-mimicy. The open problem is that can we further optimize the performance of the general monomial prediction, or we use the number of the trials to do more accurate predict? Also, except for the algebraic degree, how can we use the information of the algebraic structure to design more powerful attack? So this is the end of the presentation, and thanks for the listening.
Thank you very much. Are there questions for Jamin? Okay, this talk is slightly outside my area of expertise, but I do have a question. So you said that you've been using SMT solvers, and I was wondering, two outcomes that you can get is SAT or unsat, and then you're happy. And the other outcome is that you're running out of memory, or that you're running out of, like, getting into a timeout, which is actually quite often the case. So I was wondering, what was your experience on running those, and how long did it take, and how often did you run into this trouble of actually, well, running out of memory or running for weeks and not getting any result?
So for mimicy and festomimicy, it takes around 5 minutes to run the code with 8 threads. And for G-mimicy, it takes around 1 day to run the code.
Okay, and that is with that's with reasonable memory requirements, like, I don't know, a couple of gigabytes, or is that with a big machine with terabytes of memory?
Yes, the memory is reasonable.
Okay. Thank you very much. Any more questions for Jamin? If not, then please join me in thanking Jamin and all speakers of this session again.